So today we'll discuss another very important function in mathematics, and which is a logarithmic function. There are many applications of logarithmic function in our day-to-day life. Suppose we have to calculate pH value of a solution, or if I have to find intensity of an earthquake using a Richter scale, or even decibel level in sound, they are all instances of logarithmic function. But it was not for these applications logarithm was invented. It was around 400 years back, when there were no computers or no calculators, no approximation results, no Taylor's or Maclaurin series. People used to do lengthy calculations all by themselves. So it was then a mathematician named John Napier. He thought of this idea of simplifying calculations using logarithm. So I'll take up an example to illustrate his idea of logarithms. So suppose I have to multiply two numbers, and suppose I say numbers are 512 and 1024. I can simply write 512 as 2 to the power 9, and I can write 1024 as 2 to the power 10. Now if I have to multiply them, all I need to do is I'll just need to add these two powers. So I'll write it as 9 plus 10, and this is 2 to the power 19. Now in this case, this multiplication was simple because I was able to write both the numbers as exponent of 2. So John Napier said, if I have to multiply two numbers x and y, and if there is a way with which I can express this x as n to the power a, and I can express this y as n to the power b, then in order to multiply these two numbers, all I need to do is I'll just need to add the two powers. So for his idea to work, he'll actually need to find a way with which he can convert every number to the form of n to the power a, and then again he'll also need to find a way with which he can convert this n to the power a plus b again in some numeral form. So it took him around 20 years. He worked out a table which is called as logarithmic table. So using his log table, he was actually able to express every number as some exponent of a chosen base n, and then using his table, those numbers can again be changed from n to the power a plus b to a simple numeral form. So the Napier's idea of logarithm is to change every number as exponent of a fixed number n, and if we can do that, then multiplication, even division. So I can write it as n to the power a upon n to the power b, which is simply n to the power a minus b, which again I can convert it to z, or exponentiation. Suppose x to the power y, n to the power a to the power y, which is n to the power ay, which again I can convert to z. All these calculations, they simplify using his logarithmic table. So his idea of logarithm was taken up by another mathematician, Briggs, and together Napier and Briggs worked out a logarithmic table, but then at a very convenient base, and that was to the base of 10. So the painstaking work of Napier's and Briggs appeared very useful, especially for the astronomers, and this is how the idea of logarithm flourished. So now we can introduce logarithm. Suppose I have any number x, and I can write this number x as n to the power a, where n is the fixed number which I have chosen for my log. So we call this n as base of a logarithm. Then a log is defined as log x to the base n, and this n we write it in the subscript log x to the base n, and this log x to the base n is actually nothing but the exponent of n, which is equal to x. So basically log x to the base n is simply a. So basically log of a number x to the base n is that power of n which will make it equal to x. Say for example, suppose I have to write log 16 to the base 2. Now clearly base of this logarithm is 2 and the number is 16, and what I do know is 16 is actually 2 to the power 4. So the log of 16 to the base 2 is simply 4. So I'll take another one. Suppose I have to write log 0.01 to the base 10. So what I do know is 0.01 is 10 to the power minus 2. So basically log 0.01 to the base 10 is minus 2. So essentially log of a number about any given base n is nothing but the exponent of that number n, which is equal to x. And this is how the idea of logarithm was invented. The modern idea of logarithm was given by the king of mathematics himself, Leonhard Euler. So Euler has actually expressed logarithmic function as an inverse function of given exponential function. So suppose I have logarithmic functions such as log x to the base n, and this is equals to some number a, then by definition we know that this is x equals n to the power a, which is an exponential function. So exponential function and logarithm function, they are inverse functions of each other. Now there are two common bases that we generally use in log. So one of the bases base 10, and we write it as log x to the base 10, and also abbreviated as lgx. So when I say simply lg, so it means it is to the base 10 and it is called as common logarithm. So this is basically the logarithm that we use in simplification of calculation using log table. And the other important base that we generally use is the base e, and e is 2.7 something. So we write it as log x to the base e, or simply abbreviated as ln x. Now this logarithm to the base e is also called as natural logarithm. Now any logarithmic function is an inverse of exponential function. So if log x base a is equal to b, then simply x is a to the power b. Now any exponential function, it is always positive. So which gives me my first restriction, and that is this x should be greater than 0. Now the second restriction that we'll have in log is on this base a. Now this base a has to be positive, because for negative numbers, a to the power b may not be defined. And the third restriction is the value of a must not equal to 1. Because if I take a as 1, then no power of 1 is going to make it equal to 2. So base cannot be 1. So there are three restrictions. X should be greater than 0, a should be greater than 0, and a is unequal to 1. And together these three conditions, they give the conditions for domain of a function. Now suppose I have to find domain of a function which is expressed as log 3 minus x to the base x minus 1. So there are three conditions. First, x should be greater than 0. 3 minus x greater than 0, which will give me x is less than 3. Second condition, base should be greater than 0. X minus 1 should be greater than 0. That is, x is greater than 1. And the third condition, that base, which is x minus 1, should not be equal to 1. That is, x is unequal to 2. So if I take the intersection of these three conditions, the result I'll get is x, it should be less than 3. X should be greater than 1. And x should not be equal to 2. So the values which are common to all the three conditions is x belongs to 1 to 2 union 2 to 3. Or I can also write it as x belongs to from 1 to 3 except 2. So this is how we can define domain of logarithmic functions. I'll take up an example. Suppose I have to find domain of the function which is log x square minus 3x plus 10 to the base 1 minus fraction part of x. So this curly brackets, they represent fraction part function. Now again, I'll take up the three conditions. So the first condition is x square minus 3x plus 10, it should be greater than 0. Now for this quadratic expression, the value of d is 9 minus 40, which is minus 31. And in this case, d is less than 0 and coefficient of x square is positive. So that means this quadratic expression is positive for all x belongs to R. Now for the condition of base, 1 minus x square should be greater than 0. That is, fraction part of x should be less than 1. And by definition, we know that any fractional part function will always lie between 0 and 1. So that means this is again true for all x belongs to R. Now the third condition is a should not be equal to 1. So which is 1 minus fraction part of x should not be equal to 1. Fraction part of x is unequal to 0. Now for any number, fraction part is 0 when the number is an integer. So that means the condition I'll get is x is not an integer. So if I take the intersection of all three conditions, condition I'll get is x belongs to R minus z. So x can take any real value except integral ones. So the question is, find the domain of the function log x into x square minus 1 to the base 2 minus mod of x. So again, the first condition, which is x into x square minus 1 should be greater than 0. X x plus 1, x minus 1 greater than 0. So the roots are minus 1, 0 and plus 1. Sign of the rightmost plus, plus and plus, which is plus. So plus, minus and minus. So I need greater than 0, which is plus. The condition I'll get is either x should lie between minus 1 and 0, or it should be greater than 1. Now second condition for its base. So condition for base will be 2 minus mod x should be greater than 0, which is mod of x is less than 2. Now in previous classes we have already studied property based modulus inequalities. Now when mod x is less than a, then x lies between minus a and plus a. So from here I'll get x should lie between minus 2 and plus 2. And the third condition, which is a should not be equal to 1, which is mod of x should not be equal to plus 1, that is x is unequal to plus or minus 1. So now I need to take the intersection of all the three conditions. So what I'll do is I'll draw a number line and I'll write all the three solutions. So x lies between minus 1 and 0, or x is greater than 1, or x lies between minus 2 and plus 2, and then x should not take a value minus 1 and x should not take a value plus 1. So the region which is common to all the three conditions is this one and that one. So answer to this question will be the domain of this function is from minus 1 to 0 union 1 to 2. So this is how we can find domain of any logarithmic function. So there are three conditions. First, x should be positive, base should be positive, and base must not be equal to 1. Now as we have studied in the previous lecture that modern definition of log associates logarithms with exponential functions. So what we will study now is how to take anti-log of a given logarithm. Say for example, if I'm given some log and which is log x to the base a, and this is equal to some number n, then what I know is by definition n is the exponent of a, that is equal to x. So I can simply write it as x is equal to a to the power n, and this operation is called as inverse operation of log, and we also call it as anti-log. Now say for example, suppose I am given log x base 2 equals 5. I can take this 2 on the right hand side and I can write this x as 2 to the power 5, which is 32. I'll take another example, which is log x base 5 is equal to minus 2. Then x is 5 to the power minus 2, which is 1 upon 25. So when I remove log, so if I need to remove log, I need to use anti-log. Now there are many questions which are based on anti-log. I'll take up a simple example. Say for example, now suppose the question is solve for x log x square minus 12x plus 36 to the base 10, and this is equal to 2. So what I know is I can remove log by taking anti-log. I can write it as x square minus 12x plus 36, and this is 10 to the power 2. So I'll write it as x square minus 12x. Now 100 minus 36 is minus 64, and this is x minus 16, x plus 4 equals to 0. So that is the value of x is either 16 or the value of x is minus 4. So answer to this question is the value of x is 16 or minus 4. I'll take up another question. Now this question again is solve for x. So what I'll do is I'll take this e, I'll take anti-log. I can write it as log to the base 5, and this is under root of 2x minus 2 plus 3, and this is e to the power 0, which is 1. Now again I'll take anti-log for this 5. So I can write under root of 2x minus 2 plus 3, and this is 5. So under root of 2x minus 2 is equal to 2. Now if I'll square, I'll write 2x minus 2 is equal to 4. So which is x is equal to 3. So answer to this question will be the value of x should be equals to 3. Now another question is again solve for x, which is 1 by 12 log x base 10 whole square is equal to 1 by 3 minus 1 by 4 log x base 10. So what I know is
This equation is actually a quadratic equation in log x to the base 10. So what I'll do is I'll let log x to the base 10 as some y, and I can rewrite it as y square upon 12 1 by 3 minus 1 by 4y. I can take LCM, so y square upon 12, and this is 4 minus 3y upon 12, so which is y square plus 3y minus 4 equals to 0, and I'll write it as y plus 4, y minus 1 equals to 0. So value of y is either minus 4 or value of y is 1. Now I need to find value of x. So what I'll do is I'll substitute the value of y. So y is log x base 10, and this is minus 1. So in this case it'll be x is equal to 10 to the power minus 4 or log x base 10 is equal to 1. And if I take antilog again, I can get this x as 10. So value of x is either 10 to the power minus 4 or the value of x is 10. Now the question is find the domain of this function, which is expressed as log base 7, log base 5, log base 3, log base 2 and 2x cubed plus 5x square minus 14x. Now there are three restrictions in log. The first condition is x should be greater than 0. So for this outermost log, I'll take this as x and I can write log to the base 5, base 3, base 2, 2x cubed plus 5x square minus 14x should be greater than 0. Now I'll take this antilog. So I'll write it as log 3 log 2, 2x cubed plus 5x square minus 14x should be greater than 5 to the power 0, which is 1. Now again I'll take antilog for this 3. Log 2, 2x cubed plus 5x square minus 14x should be greater than 3 to the power 1, which is 3. Now again I'll take antilog. 2x cubed plus 5x square minus 14x is greater than 2 to the power 3, which is 8. So I can express this inequality as 2x cubed 2x cubed plus 5x square minus 14x minus 8 is greater than 0. So now it is a polynomial inequality. Basically it's a cubic inequality, and we have already studied in previous lectures how to solve polynomial inequalities. Now for a cubic inequality, now the first thing that I need to do is I need to find one value of x using trial and error method. So if I put x as 2, in this case this expression is 0. So that means one of the factor of this expression is x minus 2. We have also studied synthetic division in previous lectures. So what I'll do is I'll write it as 2. Now the coefficients of x are 2, 5, minus 14, minus 8. So first one is 0, so which is 2, then 4, 9, 18, plus 4, this is 8. So remainder, it must always be 0. So I can write it as x minus 2 into, and this is 2x square plus 9x plus 4, and this should be greater than 0. So I can factorize this quadratic expression as x minus 2, 2x square plus 8x plus x plus 4 should be greater than 0. X minus 2, 2x plus 1, x plus 2, x plus 4 should be greater than 0. So the roots are minus 4, minus 1 by 2 and 2, and this is plus, minus, plus and minus. What I need is plus. So the domain of this function will be x belongs to minus 4 to minus 1 by 2 union 2 to infinite. Now we'll discuss properties of logarithms. So the first property that we'll need to study is log 1 to the any valid base a. Now any number to the power 0 is 1. So log 1 at any valid base will always be 0. So be it log 1 base 10 or be it log 1 base e or log 1 base 1 by 2, every time when I say this log 1 to the base a, it will always be 0. Now the second property is log a to the base a. Now which power of a is equal to a? So obviously a to the power 1 is a. So in this case, if I have the same number as the base, then log a base a will always be 1. So log 10 base 10 is 1. ln e is 1. Log 0.4 to the base 0.4 will also be 1. So for any valid number a, log a to the base a will always be 1. Now the third property is log m plus log n is equal to log m into n. So if we have same base a, then simply log m plus log n is m into n. Log m minus log n, and that will be simply log m by n. So that means if we have log on the same base a, and if I'll add them, then it will be simply m into n. And if I'll subtract them, then it will be simply m by n. Say for example, suppose I say log 2 base 10 plus log 5 base 10. Now for both the log expression, base is same. So this is log m plus log n. I can simply write it as log m into n, which is log 10 base 10. Now log a base a, it is 1. So the value of log 10 base 10 will be 1. I'll take up another example. Say for example, so let log 6 base 2, log 5 base 2 minus log 15 base 2. Now base for all the three expressions is same, which is 2. So I can write as log 2. Now log m plus log n is log m into n, 6 into 5. And then minus is division, so which is 15. So I can write as this is log 2, and this 30 by 15 is 2. So log 2 base 2 is 1. So I can simplify the expressions using these two properties. Now the fifth property is log m to the power n. Now here we have n raised to the power m. So the property says I can take this n out. I can simply write it as n, and this is log m to the base a. We can also use this property other way around. So if I have n log m base a, so I can take this n to the power of m. Say for example, suppose I have log x cubed to the base 2. I can take this power out. I can write it as 3 log x base 2. If I have, suppose 2 log 3 base 2, I can take this number and I can take it to the power of 3. I can write it as log 2 into 3 square, and which is log 9 base 2. So if I have log m to the power n base a, I can simply write it as n log m to the base a, or if I have n log m to the base a, I can write it as log a m to the power n. Now there is one thing that we need to note, and which is, suppose if you have any even power, say for example, and the property says I can take this 2 out. So the result I'll get is 2 log x base 10. Now this result is essentially incorrect. The reason that for this log x square, the condition will be x square should be greater than 0. So the square of any number is essentially greater than 0. So that means the only condition I'll get is x should not be equal to 0. But on the right hand side, when I look at this log x, here the condition I'll get is x is greater than 0. So in this case, the domain on the left is not same as domain on the right. So that means if I have any condition where I have an even power, say for example, log x square to the base 10, so then I need to write it as log mod x to the base 10. So 2 into log mod x to the base 10. So we'll have to use mod x in place of x. Now these two expressions, they will be equal. Now the sixth property is when exponent is on base. Say for example, log m to the base a to the power n. Now here we have exponent on base, which is a to the power n. Now if the exponent is on base, I can simply write it as 1 by n. So this n, it again comes out, but because it is in the base, I need to write it as 1 by n. So this is 1 by n log m to the base a. Now say for example, suppose the question is log 8. Suppose the question is log x plus 2 to the base 8. I can write it as log 2 cube x plus 2. Now because exponent is in base, I can write it as 1 by 3 log x plus 2. So now here also when I have an even power, say for example in this case, so in this case again when I take this number out, so if I write 1 by 2, I'll simply have to write it as log 3 to the base mod x in place of x. A, then simply log m plus log n is m into n. Now how do we prove that? So what I'll do is I'll let log n base a as some x, and I'll write log n base a as some y. Now if I'll take antilog, I can write m as e to the power x, and I can write n as e to the power y. Now if I'll multiply this m and n, I'll get m into n as e to the power x into e to the power y, which is e to the power x plus y. Now if I'll take log, now which power of a is equal to m into n? So this is x plus y, and x is log m to the base a, and y is log n to the base a, and therefore I'll get this property, which is log m plus log n is equal to log m into n. Now what if I divide them? So if I divide it, I can write it as, m by n as e to the power x upon e to the power y, which is e to the power x minus y. So which will give me my fourth property, and which is log m minus log n, and that will be simply log m by n. So that means if we have log on the same base a, and if I'll add them, then it will be simply m into n, and if I'll subtract them, then it will be simply m by n. Now the fifth property is log m to the power n. Now here we have n raised to the power m. So the property says I can take this n out. I can simply write it as n, and this is log m to the base a. We can also use this property other way around. So if I have n log m base a, so I can take this n to the power of m. So what I'll do is I'll take this log m base a as some number, maybe x, and I can write m is equal to e to the power x. Now if I take m to the power n, so it will be e to the power x to the power n, and I can write it as a m into x. Now if I take log, I can write it as log a m to the power n. So what power of a is equal to m to the power n? So that power is n into x, and this is n, and what is x? X is log m to the base a. Now the sixth property is when exponent is on base. Say for example, log m to the base a to the power n. Now here we have exponent on base, which is a to the power n. Now if the exponent is on base, I can simply write it as 1 by n. So this n, it again comes out, but because it is in the base, I need to write it as 1 by n. So this is 1 by n log m to the base a. Now how do we prove this property? So again what I'll do is I'll write this log m base a as x, so that is a to the power x is equal to m. Now I will take nth power, I can write a x to the power n is equal to m to the power n. So I can write a x n is m to the power n, or a to the power n into x is equal to m to the power n. Now if I take log both sides to the base a to the power n, I can simply write it as log a to the power n into x m to the power n, a to the power n. Now the property says I can take this out. So I can write it as log a to the power n base a to the power n. And in this case, I can write n log m to the base a to the power n. Now log a base a is 1, so this is simply x. I can take this n on the left hand side, I can write it as x by n, and here I'll write it as log m to the base a to the power n. Now x is log m base a, so that is I can write it as log m to the base a to the power n is 1 by n into log m base a. So if the exponent is on base, then it is 1 by n log m base a. So let us take up an example. Suppose the question is log a plus b upon 3 is equal to 1 by 2 log a plus log b, and the base of log is e throughout the question. Now what I see here is, I see this property which is log m plus log n, and that is log m into n. So I can write it as log 1 by 3 into a plus b, and this is 1 by 2 log a into b. Now I do see another property n which is 1 by 2 into log m. So I can take this to the power of log. So I can write it as log 1 by 3 a plus b, and this is log ab to the power 1 by 2. Now we have logarithmic expressions and the base is same, so I can cancel log with log. So I can write a plus b upon 3 is equal to under root of ab. Now I'll square it. If I'll square it, I'll get a square plus b square plus 2ab upon 9 is equal to ab. So if I'll simplify, I can write it as a square plus b square is equal to 7 times ab. So if I'll divide it by ab, I can write it as a square plus b square upon ab, and this is equal to 7. So the question is, if log 2 base 7 is equal to m, then express log 28 to the base 49 in terms of m. So what I'll do is, I'll write log 28 to the base 49 as log. Now I express 49 as 7 square. Now there is an exponent on the base, so I can take this base out. So I can write 1 by 2. So I can take this power out. I can write it as 1 by 2 log 28 to the base 7. Now I can also write this 28 as seven into 2 square. Now log m into n is log m plus log n, so I can write it as log 7 base 7 plus log 2 square base 7. Now log a base a, which is 1, so I can write it as 1 by 2, and this is 1 plus, now here it is log n to the power n, so this n will come out, so I'll write 2 and then log 2 base 7. So now log 2 base 7 is m, so I can express it as 1 plus 2m by 2. So log 28 to the base 49 is 1 plus 2m by 2. Now the question is, calculate the value of 4 into 3 log 81 by 80 to the base 2 plus 5 log 25 upon 24 to the base 2 plus 7 log 16 upon 15 to the base 2. Now in any logarithmic question, all I need to do is, I'll just need to identify the property which I can use in a given question. Now here what I see is, I see these numbers, and these numbers, they are multiplied to log. So my property says I can take these numbers to the power of given logarithms. So I can express it as 4 into log 81 upon 80 to the power 3 log 25 upon 24 to the power 5 plus log 16 upon 15 to the power 7. And what I'll also do is, I'll express each number as powers of prime. So I can write it as 4, and this is log 2, and this is 3 to the power 4, 2 to the power 4 into 5, 5 square, 2 cube into 3, and then this is to the power 4, 5 into 3 to the power 7. So now I'll multiply these powers. So I can write it as 4. Now this is 3 to the power 12, 2 to the power 12, 5 to the power 3. This is 5 to the power 10, 2 to the power 15, 3 to the power 5. To the power 28, 5 to the power 7, and 3 to the power 7. Now another property that I see is, because the base is same, log m plus log n. Now log m plus log n is log m into n. So I'll multiply everything, right? So I'll write 4 log 2, and this is 3 to the power 12, 2 to the power 12 into 5 to the power 3, 5 to the power 10, 2 to the power 15 into 3 to the power 5, and 2 to the power 28, 5 to the power 7, and this is 3 to the power 7. Now 3 to the power 5 into 3 to the power 7 is 3 to the power 12, so you'll get cancelled. Now 5 to the power 3 into 5 to the power 7 is 5 to the power 10, which gets cancelled. Now this is 2 to the power 28, and this is 2 to the power 12 plus 15, which is 27. So what I'll get is, I'll get this simply as log 2 base 2, and log 2 base 2 is simply 1. So answer to this question is 4. Now the question is, find the value of 6 plus log 1 upon 3 root 2 under root 4 minus 3 root 2 under root 4 minus 3 root 2. It goes on up to infinite to the base 3 by 2, and I need to find its value. So what I'll do is, I'll start with this series. So I'll write this as 1 upon 3 root 2 under root of 4 minus 1 upon 3 root 2 under root of 4 minus 1 upon 3 root 2 as some number, maybe x. Now because it is an infinite series, I see this pattern: 1 upon 3 root 2 under root 4, 1 upon 3 root 2 under root 4, 1 upon 3 under root 2 under root 4. So what I know is, because the series continues up to infinite, I can also write this one as x. So I'll express this as 1 upon 3 root 2 under root of 4 minus x, and this is equal to x. Now I'll square it. If I'll square it, I'll get 4 minus x, and this is 9 into 2, 18, 18x square. So which is 18x square plus x minus 4 equals to 0. So this is 18x square plus 9x minus 8x minus 4 equals to 0. So 9x minus 4 into 2x plus 1 equals to 0. So I'll get the value of x as either 4 by 9 or x as minus 1 by 2. Now because x is equal to a positive square root, it cannot take a negative value. So in this case, the value of x is 4 by 9. So now I'll substitute this value of x. So my expression reduces to 6 plus log base is 3 by 2, and the value of x is 4 by 9. Now I can write this 4 by 9 as 2 by 3 square, or I can write it as log 3 by 2 to the power minus 2. Now the property says I can take this minus 2 out, and log a base a will be 1. So I can write 6 minus 2, and the answer will be plus 4. Now another question is, if log a upon b minus c equals log b upon c minus a equals log c upon a minus b, then find the value of a to the power a, b to the power b, and c to the power. So what I'll do is, I'll take up these and I'll put it equal to some number k, and then I can simply write it there. And then I can simply write it as log a is equal to k into b minus c. If I'll take antilog, now this is base 10, so I can simply write this a as 10 to the power k into b minus c. In the same way, I can write this b as 10 to the power k into c minus a, and I can write c as 10 to the power k into a minus b. Now if I'll take a to the power a, I can write it as 10 k b minus c to the power a, which is a to the power as 10 to the power k, ab minus ca. In the same way, b to the power b is 10 to the power k, bc minus ab, and c to the power c is 10 to the power k, ca minus bc. Now I'll multiply them. So if I'll multiply them, I can write it as a to the power a into b to the power b into c to the power cs 10 to the power k, ab minus ca into 10 to the power k, bc minus ab into 10 to the power k, ca minus bc. Now I can add all of them. So I can take k common and I can write it as ab minus ca plus bc minus ab plus ca minus bc. Now ab, it gets cancelled, ca and then bc also gets cancelled. So this is 10 to the power 0 and 10 to the power 0 is 1. So answer to this question is 1.
Now the question is, solve the system of equations log x base a log xyz to the base a equals 48, log y base a log xyz to the base a equals 12, and log z base a into log xyz to the base a is equal to 84. Now, if we look closely into this question, what we know is there's some symmetry in the question. So if I add all of them, then log xyz to the base a, I can take it common. And then I'll get log x plus log y plus log z. That will again give me log xyz, and I can find the value of log xyz. So what I'll do is I'll add all the three equations. So if I'll add all three equations, I'll get log x, log y plus log z, and I'll take this log xyz to the base a common, and here I'll get 48 plus 12 plus 84. So this is log m plus log n, which is log m into n. So I'll get this as log xyz, and this again is also log xyz, and if I'll add them, I'll get this as 144. So basically I'll get log xyz whole square is equal to 144. So that is log xyz is equal to plus or minus 12. In our case 1, if I take log xyz as 12, then if I'll put log xyz in the first equation, I'll get log which is log x base a equals 4, then x is e to the power 4, and if I'll put it in the second equation, I'll get log a base y into 12 equals 12, which is log y base a is equal to 1, then y is simply a, and in the third equation I'll get log z base a into 12 equals 84, so which is log z base a equals 7, then z is a to the power 7. So one of the solution of this equation is a to the power 4, a and a to the power 7. Now if I'll take the second case, which is when log xyz equals to minus 12. So in that case, I'll get the same result but with the negative sign. So in that case, answer I'll get is x is a to the power minus 4, y is a to the power minus 1, and z is a to the power minus n, which is 1 upon a to the power 4, 1 upon a, and 1 upon a to the power 7. So again, just by putting the value of log xyz in the equation, I can get the value of x, y, and z. So there are two solutions to this system of equations. Find the value of x if x plus log 1 plus 2 to the power x base 10 equals x log 5 base 10 plus log 6 base 10. Now what I'll do is I'll write this x as, so this is x, and I know log 10 base 10 is 1, so I can write it as x log 10 base 10 plus log 1 plus 2 to the power x base 10 x log 5 base 10 and log 6 to the base 10. Now I can take this x to the power of 10. In the same way, I can take this x to the power of 5. So I can write it as log 10 to the power 10x log 1 plus 2 to the power x log 5 to the power x log 6. Now we'll use the property of logm plus logn. So I can write it as log 10 to the power x into 1 plus 2 to the power x, and here I'll write log 5 to the power x into 6. Now base is same, so I can cancel log with log. So I can write 10 to the power x into 1 plus 2 to the power x is equal to 5 to the power x into 6. Now I'll take this 5 on left hand side. So I can write it as 10 to the power x upon 5 to the power x into 1 plus 2 to the power x, and this is 6. This is 2 to the power x. 1 plus 2 to the power x is equal to 6. Now it's a quadratic equation in 2 to the power x. So I'll let 2 to the power x as y. So I can write it as y plus y square is equal to 6. So, which is y square plus y minus 6 equals to 0. And this is y plus 3, y minus 2 equals to 0. So that is the value of y is minus 3 or value of y is 2. So now I'll put the value of y. So either 2 to the power x equals to minus 3 or 2 to the power x equals 2. Now exponential function cannot be negative. So there is no solution in the first case. Now when 2 to the power x is equal to 2, clearly the value of x is 1. So answer to this question is x equals 1. Now this question again is solve for x. So the equation is log 4 1 plus 1 upon 2x log 3 is equal to log x root of 3 plus 27. Now what I'll do is I'll take this 1 plus 1 upon 2x and I'll take it to the power of 3. So I can write it as log 4 plus log 3 and power is 1 plus 1 upon 2x, and this is log x root of 3 plus 27. Now I can use the property logm plus logn. So I can write it as log 4 into 3 1 plus 1 upon 2x, and this is log x root of root 3 and plus 27. Now I can cancel log with log. So I can write it as 4 into 3, and this is 3 to the power 1 upon 2x. I can write this as 3 to the power 1 upon x and then plus 27. So this is 12. This is 3 to the power 1 upon 2x. I can write this as 3 to the power 1 upon 2x square and plus 27. So now it has become quadratic in 3 to the power 1 upon 2x. So what I'll do is I'll let 3 to the power 1 upon 2x as y. So I can write it as 12y equals y square plus 27. So it will be y square minus 12y plus 27 equals 0. I can factorize it as y minus 3, y minus 9 equals to 0. So that is value of y is either 3 or value of y is 9. Now I'll put the value of y. Y is 3 to the power 1 upon 2x. So either 3 to the power 1 upon 2x is equal to 3 to the power 1 or 3 to the power 1 upon 2x is equal to 3 to the power 2. So if I'll compare the powers, I'll get 1 upon 2x is equal to 1. That is, the value of x is 1 by 2 or 1 upon 2x equals 2. That is, the value of x is 1 by 4. So in the question, one of the expression is x root of 3. So when they have mentioned x root of 3, so it simply means this x, it should be a positive integer. Now in this case, the values of x that I'm getting, they are fractions. So that means there is no solution to this equation.